Alrighty then, let's talk about nomenclatures. This is the third section of chapter 2 and the last one also. This is also the biggest one, okay? So buckle up, or you can do it in two portions as you wish. But nomenclature is a big deal, okay? So just like, I would like to learn the names of as many people as I meet. Similarly, you need to learn the names of the compounds that you meet this semester or more. And it's easier. Okay, so learning the names of people is much harder than learning the names of compounds. Okay, because there's a systematic way on how you actually name compounds. Okay, so we'll go through all of this. There are different kinds of compounds I'm going to go through with you is different kinds of compounds. And because of that, there are different ways on how you name things. So there are different rules for naming different types of compounds. So remember, there's metals and non-metals in the periodic table. So if you're dealing with metals, you name it in certain way. If you're dealing with non-metals, you name in certain way. Transition metals are different. So all that kind of nomenclature is kind of different. But since there is a systematic way of doing things, it becomes a little easier. Okay, so you need to learn the principles. The rest will all come to you slowly. Okay. And you know my rules. Practice, 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 everything. Okay, so first of all, let's talk about bonding. Okay, we will do bonding a lot later in the semester, but for now, I just want to introduce bonding to you because it will help you with your nomenclature also. So there are two kinds of bonding we talk about. One is ionic and one is covalent. So ionic is between metal and non-metal. And then the reason I'm saying this is because this will help you with the nomenclature, as I said. Once you see that, okay, this compound has a metal and a non-metal, then your frame of mind will be that, oh, I have to name it this way. Okay, and that's why you really need to know your periodic table, where the metals are and where the non-metals are, because then it'll be easier for you, right? It'll go faster also for you with the nomenclature. So ionic is between metal and non-metal. It involves the transfer of electrons. So I've already introduced electron transfer to you just a little bit, that you can have positive and negative substances, which are called ions. And those ions then are specified into cations and anions. Cations are positive, anions are negative. Okay, so this is all for ionic bonding. That's why they have ions. Covalent bonding is only between nonmetals. With nonmetals meaning on the right hand side of the periodic table, and hydrogen, don't forget the hydrogen on the left side. So it's between nonmetals only. There is sharing of electrons and there are no ions in the covalent, okay, compounds. Now, I'm not going to go over bonding, but I will have to do just a little bit, okay, of it. We later on have a whole chapter on this. So right now I'm just going to go through very little stuff so you understand how it's all done and it's easier for you then, okay? All right, just a few things over here that I want to mention. And again, if you don't remember every single thing of this, it's fine. Okay, I'm going to tell you what's important. All right. So first of all, covalent compounds are called molecules. All right. They are the just the nomenclature of it, just the naming of it. So when you say to me, oh, I'm talking about this molecule, immediately I know you're talking about a covalent compound. Okay, when we are talking about ionic bonding, they're actually called formula units. Okay, because it's a unit of something, a unit of plus and minus. How many pluses and how many minuses are there? That's going to be the unit. Okay, now generally we don't say, oh, I'm talking about this formula unit. Okay, so what I do for myself and for you for right now for our sanity is I just call everything a compound. Okay, this is a compound, so I don't refer to it as a molecule or a formula unit. I mean, I can call it a molecule, but I definitely don't say this is a formula unit. But I need you to know that there is actually a very specific way of identifying ionic compounds and covalent compounds, okay, by calling them formula unit or molecules. But then again, just for us, for our sanity, we'll just call them all compounds. And when you look at that compound, then you can say, oh, this is ionic or covalent, okay, by knowing whether it's metal, non-metal, or just non-metals, okay? All right. So this is something that, if you want to remember, it's fine. If you don't, it's okay. But anyhow, metals only form compounds with the non-metals if the metals are with other metals. They're called an alloy. It's a mixture then, okay? That mixture could be homogeneous or heterogeneous, usually homogeneous mixture, but it's called an alloy. On the other hand, non-metals will combine with other non-metals, okay? Do you see the difference? All right, so metals can not combine with metals, but non-metals combine with each other actually in a proportion, okay? And then finally, the last thing here, that this is really critically important, so if you have your printout, you can put a star on this and highlight it, is that there are 7 diatomic gases, okay? And these gases, they have the same name as the element, okay? So for example, hydrogen is H on the periodic table, but it is also H2. Similarly, O2, N2, F2, Cl2. The last 4 here, these are all the halogens. Okay, halogens meaning group number 7. F2, Cl2, Br2, I2. Okay, they don't exist as I. This nitrogen does not exist as N on this earth. Okay, so on earth, all of these are what we call diatomic gases, because first of all, well, called molecules, all right, because up to here, up to chlorine, these are all gases. Bromine is a liquid and iodine is a solid. So diatomic molecules, you can call them, or some of these are gases, so you could call them that too. But you have to know this, okay? Now, when do you know you're dealing with hydrogen as an H and hydrogen as an H2? That depends on the question, okay? And so as we go through our chemistry, I will try to tell you that here you're dealing with hydrogen as atomic hydrogen, and here you're dealing with hydrogen as a gas, as a molecule, okay? You will learn to identify that as you go through, okay? So don't think it's going to be a problem. Will be a problem if you make it, okay? So don't make it. All right, so let's talk about ionic compounds. Now, ionic compounds can be 2 different kinds, all right? So there is the main group, ionic compounds, and then there's transition metals also, okay? And so we will learn both of them separately. So first of all, let's talk about the main group, okay? Remember, in main group, you have 8 groups, and on the left-hand side, you have the alkali metals and then alkaline earth metals, and then group number 3, which partially has the metalloids in it, okay? So group 1, the cation you form from group 1 is always going to be +1, okay? Always. Group 1, +1. Group 2 will always give 2 electrons and it will be +2. Group 3 will always be +3. These will all form cations, right? So group number 1, 2, and 3 will always form cations. Now, please make sure that you write things properly, okay? It is really important to me that you write things properly. So for example, when you're writing Na+, you should be writing it like this. Now, if you circle it or not, that's up to you, okay? But Na, this is wrong. Okay, so don't write like this. It should be a superscript, okay? The charge should be a superscript, so write it like that, not with it, okay? So that's an important thing. It's a language, okay? So learn the language of chemistry. That's how it is. Now, the non-metals, on the other hand, they will accept electrons. And remember, when you accept electrons, now there are more electrons. So now it is negatively charged. So group number 5 over here. So group number 5 is the nitrogen group, okay? That can accept 3 electrons, as you can see from here. And it becomes -3, and then P is also -3, and so on. Then oxygen group can accept 2 electrons. And then group number 7, which is the halogens, they accept 1 electron. Now, is that standard? And yes, that is standard, okay, pretty much. Well, when we establish rules, you can change those rules and you will learn new things, okay? So this is not like written in stone. Things will change, but this is what happens. Now, this will never ever change, okay? So lithium will always give that 1 electron for sure, okay? Now, nitrogen, remember, nitrogen is a non-metal. It can form covalent bond also because it's a non-metal. So it can form an ionic bond and it can form a covalent bond. So when it is covalent bond, there are no ions in there. Okay, so you have to look at it from that point of view, that you can have two different kinds of bonding. Here we are talking about ionic compounds, so that's why I'm dealing with only ions. Okay, so let's carry on then, okay, from there, so you understand how these things are. Now what I would, advise you to do is write the charges on the groups. Okay, so we will do that also later on, but if you want to get started on it, you could. Okay, so here's your periodic table, right? So group 1 is +1, group 2 is +2, and then here are the transition metals, forget those, and then +3, and then -1, -2, -3, right, for the last 3 groups. Noble gases will not form any bonds, so group number 8, we will not be talking about that, okay, at this point. So group 8 is noble, right? We don't combine with anything. We want to stay by ourselves, so let them stay by themselves. We'll talk about the other elements, okay, meanwhile. Okay, so naming compounds. So first of all, I want you to understand that a cation has the same name as the element, but you want to put ion in front of it. Okay, so for example, what I've given you over here is sodium. Sodium is sodium, right? Na. But Na plus is not the same as sodium. That is going to be sodium ion. Because if you say Na plus, but you mean Na, or the other way around, then we're not talking the same thing, and then we will misunderstand each other. So because sodium and sodium ions are very different. One can kill you, the other one maintains your blood pressure. Okay, so sodium, if you eat sodium by itself, you're going to die. Okay, because it's going to start reacting with your body very, very fast. Sodium plus, on the other hand, which is sodium ion, is something that we eat all the time as salt, and we're totally fine with it. Okay, so sodium and sodium ions are not the same things. All right, so when you say to me that, oh, I want to, eat some sodium, no, you want to eat some sodium ions probably. Okay, that's what you're probably thinking. I don't know what you're thinking, but that's what I'm thinking, that you don't want to eat sodium. Okay, so add the ion in front of the ion. If there is a charge on there, it means it changes everything. Okay, so for calcium 2+, it's going to be calcium ion. All right, for potassium, potassium ion. If it is K+, if it is just K, it is potassium. That's it, just leave it like that. Okay, all right. The anions, on the other hand, the interesting thing about anions is their name changes completely. Okay, not completely, a little bit at the end. Okay, so the name starts ending with "ide." So chlorine, for example, becomes chloride. Oxygen becomes oxide. Remember, oxygen is 2-, okay, and chlorine is -1. So the last portion over here, so chlorine is gone, the ion E is gone, the Ne is gone, I should say, and it's replaced by IDE. So it becomes chloride. So you can look at all the non-metals, and actually there are not that many. Okay, I mean, I can go through it really quickly with you. So if you look at the right side of the periodic table, you have the fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, phosphide, carbide, and then hydride on the left hand side with the hydrogen. Those are your ides, okay, that you need to know. Again, chlorine is not the same as chloride, okay, and it's really important. Again, nomenclature, naming. You would not like it if somebody calls you with a different name, okay, or messes up your name. So same thing, elements don't like it either, and actually it can mean a whole different thing, okay, if you don't call it by the proper name. Okay, so when you name ionic compounds, and remember right now what we're talking about, we're talking about main group elements, okay, and what are the main group elements? The 8 groups, okay, nothing in the middle. Those are transition metals. I'm talking about main group elements. So when you name something that is a main group element, you just take the metal name and then end it with whatever ide it is, okay? So NaCl, you see the metal and the non-metal. Metal is main group element, so it becomes sodium chloride. CaO is calcium oxide. Very simple, okay? So Now here in this case, it's a little bit different because the ratio here is 1:1, and we'll talk about that in a second also, okay? But otherwise, it's a very simple, straightforward thing. The first element does not change its name. Now here, you're not saying sodium ion chloride, by the way, okay? You're just saying sodium chloride. As soon as you say sodium chloride, I know you're talking about sodium ion automatically, because otherwise sodium will not be with chloride at all, okay? It will be by itself. Okay. So there are some exceptions. Of course, there are exceptions. You know, we learn rules and then we say, okay, there's exception. And the exception is for tin and lead. Okay, and tin and lead, they have two charges. So lead is 2 plus and 4 plus, and tin also is, 2 plus and 4 plus. And then I will add that here. So later on, I'll type it out. But, tin is 2 plus and 4 plus. So we have to change the names of that, and thallium also has that. This is not thallium, sorry, but it has to, but we don't have to worry about that too much. The tin and the lead is really what we have to worry about, okay, because we use those names a lot more, okay, for us. So no, TL is thallium, okay, just to kind of correct myself there. But anyhow, so remember that as we go on, okay, because the nomenclature, as I said, it's an important thing. We don't want to mess up naming anything. Okay, so naming compounds simply, first of all, okay, I'm going to tell you how to make them also, but right now, just to, if you look at a compound and then how to name it, so CaF2, you will just say calcium and then fluoride. You will not mention the 2. You will not mention the 2 in the K2O. So that's just potassium oxide. You have nothing to do with the 2, okay, right now. This is the rule for the main group elements, okay, and this has to do with the fact that there is no other combination possible, okay. We'll learn that in the next slide, but really that's how it is, okay. So when you're looking at the name calcium fluoride, you cannot tell by looking at the name that there are 2 fluorines in there, okay. This is something that you have to work out, because remember, in this chapter, not only are you going forward, you're going to go backward as well, which means that I can give you calcium fluoride and you have to write me the formula for it. Okay, so we have to go both ways. All right, I can give you the formula, you know the name, and I give you the name and you figure out the formula. So calcium fluoride doesn't tell you there are 2 fluorines in there, and how do you figure that out? And that's coming up now. Okay, so what we do is we do a little bit of a crisscross thing, okay? And this is good for the main group elements only, okay? So the crisscross method is really quite fantastic, okay? And this works best because you know the charges, okay? And remember, group 1 was 1 plus, and group 2 was 2 plus, group 3 is 3 plus, and then on the right hand side, the -1, -2, -3, okay? That's how it goes. So for example, if you are forming a compound between sodium and nitrogen, okay? Sodium and nitrogen, even without looking at the formula, you know that the compound between sodium and nitrogen will be sodium nitride. Okay, you know that. But now what we're trying to figure out is what is the formula for it. Okay, so the formula for sodium and nitrogen, what you do is you start writing out the different charges on it. So sodium is always +1 because it's in group 1. Nitrogen is 3- because it's in group number 5. It's always going to be 3-. So you write the charges, and then what you do is you do a crisscross with the formula. So the Na plus, the +1 goes down here, and the 3- goes down on sodium. And how does that work out for us? Okay, so let me explain that to you. So when you have Na plus, it means that it is giving 1 electron. When you have N3-, what that means is that nitrogen is accepting 3 electrons. Now nitrogen is only accepting 3 electrons, not 1, not 2, 3. So which means that you need to have 3 sodiums in order to get those 3 electrons that it can give to 1 nitrogen. And that's where this formula comes in. So now you have Na3N because you need 3 sodium for every single nitrogen. That is the formula unit that I was mentioning before. So instead of doing all of this all the time, once you do the crisscross, the arrows that you see here, the blue arrows that you see here, so once you do the crisscross, it becomes a lot easier, because now what you're doing is you're taking the superscript and making it the subscript. Okay, now when you write the formulas, again, please be very good about this. So Na3N, not Na3N, that is wrong. Okay, and if there is only one of one element, you don't write that one. So the plus one that was there, you see that I did not write 1 over there, okay, because you don't write that 1. Okay, it is understood that you have 1, at least you have 1, otherwise why would you even be writing that element, okay, in there. So next here, look out for aluminum and oxygen. Again, you can tell even by looking at anything else that aluminum and oxygen would be called aluminum oxide. So now we're just trying to figure out the formula. So again, what you do is you do the crisscross method. These charges you already know because you know your periodic table. Okay, so oxygen will always be -2. You already know that. So all you need to do now is figure out the formula. Okay, so again, you need 2 aluminum, 3+, and 3 oxygen. Oxygen is 2-. Okay, the main thing is that at the end of everything, okay, at the end of forming the compound, you should have a neutral compound. So your charges should all neutralize each other. So you have 6 electrons given and 6 electrons taken. Okay, a complete transaction, okay, in here. So there's no charge left over. That's kind of what the whole goal is here. So that is how we make compounds, okay, because you don't see any ions left over. All right, so I hope you see what I'm trying to tell you with all of this, okay. All right, so now we get into transition metals. Transition metals are a little bit different because in this case, the transition metals can give different number of electrons. Okay, so when we learn about alkali metals, we say, okay, we have group number 1. Group number 1 can give only 1 electron, right? There's nothing else, as I said to you. I mean, it's a standard thing. That is it. It's done. Group number 2 will give only 2 electrons, and that's it. So you don't have to worry about anything. And that's why I said the formula then is very consistent, because that is it. Those are the charges possible. But transition metals are a little bit different. Okay, and so for transition metals, iron can be iron 2 iron or iron 3. So which means that it can either give 2 electrons or 3 electrons. Now why it can do that, we'll talk about that later. But at this point, you just need to know it does. So it gives 2 electrons or 3 electrons. So when we say that we are forming iron oxide, well, what kind of iron is it? Is it iron 2+ or iron 3+? Or if anybody doesn't know anything, then we're like, is it +1? Maybe it's giving 1 electron. So what am I doing here? So it becomes a little confusing, all right? So in order to remove that confusion, what we do is we write a Roman numeral to indicate how many electrons have been lost, okay? So iron 2+ becomes an iron 2 ion, because then now you can clearly see that you're dealing with either a 2+ or a 3+. Okay, in there. So when we say that you have iron 2 ion, it means you know that you're dealing with Fe2+. Okay, so the Roman numeral is what we have to use for transition metals. You saw that we didn't use Roman numerals for the main group, and we don't. That is the rule. Okay, so you have to follow rules. All right, so but for transition metals, you have to use that. Once you know what the charge is, the process is still the same. Okay, which means you do the crisscross. Okay, so once you do the crisscross, you can come up with the formula. So once you know the formula, now for the name changes a little bit. You can't call it iron oxide anymore. You have to say whether it's iron 2 oxide or iron 3 oxide. Okay, so in this case, the iron is 3+, so it becomes iron 3 oxide. Okay, so you can see that from the main group to the transition metals, what has changed? the Roman numerals. Okay, and you have to use those. So here is another example that I've given you for manganese. Remember, manganese is Mn, magnesium is Mg, which belongs to group number 2. Okay, so know your elements well. So manganese can be 4 plus, 5 plus, 7 plus, 2 plus, whatever. Anyway, so too many charges to remember. So you don't have to. I will give you those, right? I will tell you because I have to. How will you know otherwise? There is no other way. Okay, so I have to tell you that manganese is 4 plus or 7 plus or whatever. So here is manganese 4 plus, which means you will write it as manganese 4 ion. Okay, in there. But anyhow, so manganese and then sulfur is always going to be 2 minus, so sulfide. So when you do the crisscross, you get 2 and 4. Okay, so now remember, you have to bring it down to the lowest ratio, or maybe I haven't talked about this yet. I don't think I have, but anyhow, you have to bring it down to the lowest ratio, which really the ratio is 1:2. Okay, so write MnS2, don't leave it as Mn2S4. Okay, so just bring it down to the lowest ratio possible. So this becomes manganese 4 sulfide. Okay, now if you look at all of this, this is still not telling you what the charge on anything is. Not the charge, it's not telling you what the ratio of anything is. Okay, so iron 3 oxide doesn't tell you that you have 2 irons in there. You still have to figure that out. Okay, so just be careful as you're going through all of these. Okay, because even in the main group, you could not tell looking at, you know, sodium chloride whether it's a ratio of 1:1 or 1:2. Who knows, right? So you figure out the charges and then you figure out the formula. Similarly here, you cannot figure out, okay, if at iron 3 oxide, how many oxygens are in iron 3 oxide? Unless you write out the formula like this, you will not know. Okay, so iron 3 oxide, how do you work with that? So if you were taking it the other way, for iron 3 oxide, you like, oh, okay, so I have iron 3, so which is iron 3 plus, and then oxide is O2 minus. Then you do the crisscross, right? And then you figure out the formula for it. So that's kind of how it works. And this is it, you know, I mean, we have to do this. There is no other way, okay, for this. Okay. So here are some solved problems. Go through it. Okay, let me know if you have any issues, but otherwise I've tried to give you a little explanation here. Also, how I am going through my thought process on forming these compounds, okay? All right, so here, this periodic table, this one has all the charges on all the ions. Now don't be fooled, okay? You don't have to memorize any of this, and also don't be fooled by all these charges on carbon, because carbon group is actually very interesting group, you know, group number 4. Okay, it's very interesting group because there is non-metals in there, and then there's metals and metalloids, everything is there, so it's a little bit different kind of a group. All right, hydrogen is a little bit different because hydrogen can give an electron, it can also accept an electron. Okay, so I said hydrogen is weird element, but otherwise everything here is consistent. See, +1 and then +2 and then -1, -2, -3. This is all very consistent. Okay, and then I've given you for tin and lead as to the +2 and the +4. The tin and lead, you treat them kind of like transition metals. Okay, so tin would be either tin 2 plus, or, you know, so tin could be 2. So if we say it's tin 2, then it would be, you will write that as tin 2 ion. Okay, that's how you would write it. Tin 4 plus would be the tin 4 plus ion, or the tin 4 ion. So you have to be careful with those two, but the other ones, theirs is pretty consistent. Okay, transition metals, I've given you all the charges on here. You don't have to remember them. Okay, that's okay, because once you look at the name, you will figure it out. Okay, so no point memorizing any of that. Okay, now we come to polyatomic ions. Polyatomic ions are ions that are made from a combination of elements. Okay, so you can have 2 or more atoms combining together, but even when they combine, they don't neutralize each other. Okay, like I was saying, you form a neutral compound, but polyatomic ions don't do that. Okay, you still end up forming an ion at the end. So for example, I have the positive one. The one I want you to remember here right now is the ammonium ion. Hydronium ion does not exist by itself. It exists only in certain solutions. Okay, so it doesn't form compounds either. So I want you to remember the ammonium ion. Okay, ammonium ion is not just that it is NH4, it's also plus. Okay, and it's +1. So that's what you have to remember. And I am really sorry for this one. Like, there's nothing else you can do but memorize all of this. Okay, there is no other thing. I'm telling you what you need to memorize and what you don't need to memorize. Okay, so I said don't worry about memorizing the charges on transition metals, but this stuff you have to memorize. Okay, so hydroxide, cyanide, these are very simple ions over here. Hydroxide, cyanide, 2 atoms and then a negative charge. Okay, what is going to be a little bit harder for you is this table over here. Okay, because there are so many polyatomic ions here, and you can see that almost all of them have oxygen in them. Okay, so these are oxygen containing polyatomic ions. There is nothing else to do but memorize their names. Okay, you have to know them. The carbonate, sulfate, and hydrogen sulfate, you have to know all of these. Okay, you treat them just like any other anion. Okay, but the only thing is it's a combined thing. You don't find them in the periodic table, obviously, because these are not elements. These are polyatomic ions, so they're a compound sort of. Okay, I've made 2 tables over here for you. The left one you have to know and memorize. The right one you don't have to. You can just use that as a guide, okay, for in case I give you anything on any assignment or you see it somewhere else. Right ones you don't have to memorize for me. The left one you do have to memorize, okay, because you see them a lot all the time. Okay, everywhere you're going to see them. You're going to see them in the lab, you're going to see them in my exams and all that. Okay, so you have to know all of these for sure. All right. Just make cards, okay, and start memorizing them. Again, as I said, there's not much else you can do. Now, how do you form compounds with them? You will form compounds with them just like you do with normal cations, okay? Because remember, these are cations and anions, so they can form compounds with cations or anions. So I've given you both over here, okay? So here is between sodium and hydroxide. So it's the ratio of 1:1. Okay, because this is +1, this is -1. So by the time you come down to 1 and 1, you just write NaOH. Okay, so it's a 1:1 thing. Now hydroxide, you should know it's a polyatomic ion because you're supposed to memorize that. So you're not looking for it on the periodic table. Where is hydroxide? It's not there on the periodic table. Okay, all right. So then here is for potassium and sulfate, and potassium is +1, so that's 1 for sulfate. Sulfate is 2-, so that's 2 for potassium, and so K2SO4, so this is 2 for potassium, 1 for sulfate. Okay, and so here you have the 1 polyatomic ion. You don't need any brackets in here because I'm telling you where you need brackets also. Okay, because when you have a polyatomic ion, sometimes you need to contain it. Okay, and this is kind of an important thing because sometimes I get really weird names. Like for this one, NaOH, you should know OH is a polyatomic ion and it's called hydroxide. And so this is not sodium oxide hydride. See what I mean? That's not a thing. All right. Similarly here, this is not potassium sulfide oxide. That just does not exist. Okay. So you have to know that SO4 is sulfate. All right. Okay, so then here we have some other combinations going on between calcium and phosphate, and calcium and phosphate will form again crisscross, and so calcium 3 and phosphate are 2. So now you're going to need those brackets, okay, in order to tell me that you have 2 phosphates. Okay, there is no way you can write it without it, because if you write, so like, calcium and then 3 and then phosphate 2, how do you write that? What does that mean? Okay, and so you have to put the brackets around in order to show that you have 2 of the phosphate ions, okay, in there. That's how it works. So, go through the other examples and make sure you know how to do this. Again, keep it simple, crisscross, okay, and keep it Simple as in memorizing all the names. Yeah, I'm sorry. Okay, this is, you can't get out of that. Okay, now let's get into covalent compounds. And covalent compounds are just a little bit easier than all the other ones, because in covalent compounds, first of all, I will never ask you to form a compound, okay? Because covalent compounds can have multiple combinations. We saw that already before with carbon monoxide and carbon dioxide. Okay, here I've given you a whole bunch of oxides with nitrogen. These are all possible. So if I say give me a formula for nitrogen and oxygen, you don't know which one to give me, all right? And so I'm not going to ask you to do that, all right? I will not ask you for forming any compound. I will ask you to name the compound, or the other way, that I'll give you the name and you give me the formula, okay? Now, the good thing is, because there are so many combinations possible, you need to know what is the ratio they are combining in. Before that, we didn't know, right? For ionic compounds, we didn't have to, because the charges were there to tell us the combination. But here we don't have the charges because covalent compounds don't have any ions in them. So for that reason, you have to use prefixes. Okay, so the prefixes will tell you how many atoms there are in the combination. So you have to again memorize this, all right? But this is not such a hard memorization, all right? So 1 is for mono, 2 is for di, then tri, tetra, and all that, up to 10, okay, up to deca, you should know. So here are some examples that I've given you for covalent compounds, and you see they're not that hard, right? So nitrogen monoxide, if the first element is only 1, then you don't have to say mono nitrogen, okay? So you don't say that, you just say nitrogen, but the second one you have to say mono, okay? So nitrogen dioxide, dinitrogen monoxide. Now, once you learn this, you want to use it for ionic compounds, but resist that urge, okay? Because no, you cannot do that, all right? So it's very common that, you know, I will teach the covalent compound nomenclature, and then when we get to calcium fluoride, you're like, this is calcium difluoride. No, it's not calcium difluoride, it is still calcium fluoride, okay? So ionic compounds have their own nomenclature and covalent compounds have their own nomenclature, okay? So resist the urge to, you know, crisscross and mismatch everything, okay? Don't skip that. It's very systematic nomenclature. And again, how do you know that you're going to name this in a covalent compound? Because they're all non-metals, okay? So when you look at all of these are all combination of non-metals. That's how you know it's a covalent compound. That's how you know you have to use prefixes, okay? That's why I'm telling you, when you look at a compound that you need to name, the first thing you should do is figure out, is it a metal, non-metal? If it is a metal, is it a transition metal? Is it a main group? Because transition metals will need the Roman numeral, okay? So, you know, there's a systematic way of doing all of these things. Okay, so here are some more examples. You can look that through as you wish. I need to keep moving on. So nomenclature of acids and bases. So acids, here are some properties. If you don't remember this now, it's okay. It doesn't matter because you're going to learn it later on also. Okay, but these are some of the properties of acids, and there are some properties of bases. We're going to do this in a later chapter. I just wrote these over here, so it kind of gives you an idea of what we're dealing with. Okay, and especially the one that I need you to know is the one about protons. Protons is actually H plus. Okay, so proton here is H plus, not H minus. H minus is hydride. Okay, so proton is H plus. So acids will give you protons, and the reason you need to know this is because all the acids we are going to write, they will have hydrogen in them. Does it mean bases don't have any hydrogens? They do, in a different way. Okay, so I've given you examples here also, okay, for the acids. So, but I haven't given you the structures. That's coming on the next slide. Okay, so here are some examples of the bases. Here are the names, and in the next slide we're going to talk about the structures of these, so you have the formulas also. Okay, so acids, there are two kinds of acids that we talk about. One is called binary acid, the other one is oxoacids, and binary is really all the halogens. Okay, so HF, HCl, HBr. Now, if you look at HCl by itself, you're going to think, oh, HCl, hydrogen is a nonmetal, Cl is a nonmetal, this should be hydrogen chloride. Why is it hydrochloric acid? And here is the key thing. This is dissolved in water. Soon as you dissolve HCl in water, it goes from being hydrogen chloride to hydrochloric acid. So if you're thinking, how am I supposed to know this? Well, I have to tell you this, okay? Otherwise, if I don't tell you this, then I have to accept your name as the hydrogen chloride. Do you see what I mean? Okay? So HCl, if I don't say that this is dissolved in water, yeah, go ahead. Say that this is hydrogen chloride. All right, but if I say this is HCl, this is made in water, you have to say hydrochloric acid. Okay, so it changed completely. All right, the name changed from hydrogen chloride to hydrochloric acid. So you kind of have to know this, okay? The good thing is you will encounter these acids a little bit, like HCl, you encounter that in the lab, that you will kind of remember. All right, the other acids like HF, HBr, we don't encounter these much because they're very strong and very dangerous for us. Okay, HCl is also dangerous, but we need this a lot more, and this is a little bit more practical, okay, than the other ones. Then the oxo acids, okay, are these ones, and if you look at them, they're actually all coming from polyatomic ions. See the nitrate, sulfate, phosphate, carbonate, okay? These are the polyatomic ions, and you add hydrogen to them and they give you the acid. But this is not nitrate anymore. The name for this is now called nitric, right? And everything is ending with acid. So nitric acid, sulfuric acid, phosphoric acid. The only thing you can say from phosphoric acid, oh, there is a phosphorus somewhere. That's all. But it doesn't tell you the combination. So you still have to figure out the combination, which actually is not very hard. So if you know what is phosphate, so phosphate is 3 minus, and as I said, proton is all H plus. So that's H plus. So when you do the crisscross that you need H3PO4. Okay, so that is how you can figure out the acids, but you have to know your polyatomic ions. In the polyatomic ions, not only do you have to remember it's PO4, but the charge also, that it's PO4 3 minus, so it's a little bit of a, memorization thing going on with that. Here's a list of how you get the oxo acids. So I've given some of these to you, okay? So I didn't write the one for hydrogen carbonate, okay? So these are the ions, okay? The polyatomic ions, and then how many hydrogens, protons I'm adding here to give you the acid, okay? So hopefully this chart makes it a little bit easier for you to remember your acids, all right? Bases are a little bit easier because most of the bases are going to be hydroxides. Okay, so here you can see this is sodium hydroxide, potassium hydroxide, aluminum all hydroxides. Some carbonates are also bases. For right now, the most common bases you will encounter are going to be all hydroxides. And remember that hydroxide is OH minus. OH minus. So it's a polyatomic ion. So whether you combine it with Ca, so in that case Ca2 plus, that's the ion. So when you're combining, you do the crisscross. So, and I think I've done this before, this is the formula that you get, okay, from there. Now with the bases, it's nothing like that, oh, they have to be in water and then they're bases. That's not how it is, okay? Acids are a little bit different, as I said before. So like HCl is hydrogen chloride, okay, but this is gas. HCl in water is acid, okay? So two different things, but calcium hydroxide is a base. Is a base, whether it is in water, not in water, it doesn't matter, okay? So at least that part is easier for bases, okay? And also with the acids, it's only for the binary acids that you have to see, oh, is it hydrogen chloride or is it hydrochloric acid? Because as soon as you see sulfuric acid, then okay, that's H2SO4, okay? So yeah, not right now, but in a little bit later, as you learn all the acids, you will know it. Okay, so You just have to remember, okay? Again, practice, memorization that you have to do. Okay, then there are some things called hydrates, and hydrates are where you actually have water molecules that are associated with some compounds. The good thing about this, you don't have to learn an entirely new nomenclature. You don't have to. So for example, these compounds over here, they actually have water associated with them. So magnesium sulfate is still magnesium sulfate. That has not changed. What has changed is that there are 7 molecules of water. So then you just have to write heptahydrate. Okay, hepta for 7 and then hydrate for water. Okay, so it's a simple kind of an addition, not all that complicated. Okay, for copper sulfate, remember copper is a transition metal. So copper will be then copper 2 sulfate pentahydrate because there's 5 water molecules. So it's not all that hard, okay, for the nomenclature. Most of the rules are the same, except now we've kind of combined a little bit of the covalent compound rule, which is, using the prefixes, okay? All right. And then finally, and yes, I know, finally, we're ending this, some common names, okay, that you should know of, which are not really, we don't think about them. Like water, for example, is actually dihydrogen monoxide, but who thinks about that, right? We just call it water, but it's actually a chemical. Salt, pass the salt. But what is the salt? Salt is sodium chloride, okay? And so these are common names that we use for compounds which we don't even think about that they're actually made of chemicals, but they are chemicals, okay? CH4 is methane, which is the natural gas which is used in your homes, for gas stoves and heating. Dry ice is carbon dioxide, yeah, a really low temperature. Okay, at that point, ammonia doesn't tell you that there is nitrogen in there or hydrogen in there, right? You can't tell. Methane, you cannot tell there is, carbon and hydrogen in there. So, these are common names. So, I would recommend that you will learn up to ammonia. So water, I know it's not a problem for you guys, okay? Methane and ammonia is the one that I would say that it'd be good for you to know, okay? All right, I think I'm done now with nomenclature. This should be it. So really a lot for you to do here, a lot for you to practice on. There are a lot of rules, so, and lots to memorize also, okay? So, all right, all the best with your memorizations.